non-linear spaces over R, where R is of course the
set of real
T of lambda x is equal to lambda T of x. So this is how we see the linear map from a vector space E. In fact, to really define a linear map, I do not need that they are non-spaces. A linear map T from E to X is bounded if and only if we can find a constant m greater or equal to 0 such that for any x we pick in E, for any x I'm assuming that the domain of T is the entire E. For any x we pick in E, we have that norm of T of x in x is less than or equal to m norm of x in E, norm evaluated in A. So whenever a linear map satisfies that condition, we'll call it what? A bounded linear map. And then one thing we need to understand that for, let me put this as a proposition. One, if T from E to X is a linear, then the following are equivalent. What are they? Number I is that T is bounded. Number I is that T is continuous, or T is Lipschitz. So these properties are the same. That is, they mean the same thing for a linear map.
Okay.
Once you establish that the linear map is bounded, then you can conclude that it's continuous. And not only that, continuous. You see this. This is perhaps the only map I've seen that continuity at just one point means continuity everywhere. Continuity at origin means continuity everywhere. So these are equivalent for a linear map. Now the question is, how can we justify this? How do we justify this? Now, let us look at the proof as follows. Proof. We assume we show that I implies I. So the way I'll go is this following. I'll show that I implies I, and that I implies I, and that I implies IV, and that IV implies V, and that V implies I. This is what I'll do. I implies I implies I implies IV implies IV. So once we're able to establish this chain, then we can conclude that the statement of the proposition is true. So let us break it into pieces. First of all, show that I implies I. So we assume that suppose T is a bounded, of course, it's a linear map.
Yeah.
So let me just say the bounded linear map. We show that T is what? Is continuous. is continuous. I think it is enough to show that if x naught in E is arbitrarily chosen, then T is continuous at what? At x naught. So if you're able to show that T for arbitrarily chosen x naught, T is continuous at x naught, then we conclude that T is what? Is continuous. Now, boundedness of T means what? Means that there is a constant m greater or equal to 0 such that for any x in what? In E, what happens? For any x in E with m num of x, this is what it means that that T is bounded. And that please let me put this what we will be looking for. T continuous at what? X naught means what? Means that for any epsilon bigger than 0, we can find what? A delta depending on epsilon and x naught. Let me call it that delta. There exists a delta which is a function of epsilon and x naught, or rather a function of x naught and what? A function of x naught and epsilon. It doesn't matter. A function of x naught and epsilon bigger than 0, such that for any x in E with that is x in E that satisfies num of x minus what? X naught less than what? Delta. Then num of T of x minus T of x naught in x will be less than what? X times. This is actually what we want to achieve. If we're able to achieve this, we conclude that T is what? Is a continuous line. So what does this mean? What means that? What it means is that we should try to compute, given epsilon bigger than 0, we should find a delta for which this will happen. For any x in E that satisfies this condition, this will happen. Remember, I'm taking E as the domain of what? Of T. I'm assuming that E is the domain of the operator T. Is given that T is bounded, we want to achieve the box. So now let epsilon bigger than 0 be what? Be given. Let epsilon bigger than 0 be given. We find delta, which is a function of what? X naught and epsilon bigger than 0. We find a delta. So that sounds like a repetition, but emphasizing an important concept makes it sake. So that what? For any x in P satisfying num of x minus x naught less than that delta, we have that num of T of x minus T of x naught and what is less than what? X naught. But T is linear and what? And bounded. Now, using linearity and boundedness of T, we obtain we obtain for some constant m greater or equal to 0 that for any x in E, norm of t of x minus t of x naught is equal to what? Norm of t of x minus x naught. This is where the linearity is playing a role. By the linearity of t, we can do this. And this is less than or equal to m norm of x minus what? X naught. Because t is what bounded. So, if norm of x minus x naught in E, sorry, if this is less than delta,
T is mapping from where to where?
t is mapping from E to x.
E to X, okay.
T is so this value is in x. That's why the norm of, I'm being careful here.
Yes.
You see, the norm that will be acting on the image, on the action, will be x.
Yes.
So coming here, we return to. You understand? But where these things are clear, where we are sure of what we are doing, there's no need specifying where.
Yes.
And the essence of doing this is for us to see that it's not only just one norm that is running. The norm in x, the norm x is endowed with, as well as the norm E is endowed with. So if this is less than delta, then it means that what? Norm of t of x minus t of x naught will be less than or equal to what? In fact, will be less than or equal to m norm of x minus x naught, which is less than what? M delta. M delta. Because this is less than delta. So that will be less than m delta. It's at this point that we can now make the choice of that word, of that delta. And watch here, please. Observe that m is greater or equal to 0. So there's possibility that m will be 0. There's a possibility that it will be 0. Then in that particular case, in making choice of delta, we also have to be very careful and we play a little trick. We play a little trick that we don't have 0 in the denominator. So when this, we will choose this in such a way that whatever remains here will be what? Epsilon. So in that particular case, we choose delta to be, if we choose delta to be epsilon over m plus 1.
M plus
plus
1,
a
yes.
positive constant. Choosing delta equals epsilon over m plus 1.
Yes.
We obtain that norm of t of x minus t of x naught. X is less than what? It's less than m epsilon over what? M plus 1, which is still less than what? Epsilon. Because m over m plus 1 is less than 1. It's less than epsilon. So what is our conclusion? So what we have is that whenever this let me do this please. Let me cast a little bit. Watch it. Less than delta. Let me throw more light here. If this is less than delta, the appropriate thing should have been so if x in E is such that this is less than delta, then this will happen. This is happening for all x in E.
Yes.
Then for those x in E for which this will be less than delta, this is what will happen. Does it make sense?
Yes.
So from there,
So that's the delta now depends on. Okay.
now look at it. Look at the idea. Look at the idea. What we're saying is the following. Assuming that this is the whole space.
Okay.
This is the whole space. Huh?
Yes.
Okay, let me read it. Let me read it so that we appreciate this a little bit. Here is the space E. And this one is the space X. Of course, X naught is fixed somewhere.
Yeah.
In E. Then X is varying in what? X is varying in E. If we now get this delta, Not all x in A will satisfy
Yeah.
x being inside this what? This ball.
Okay.
For any x in A, irrespective of where it is,
Yes.
this inequality is always true because of boundedness of what?
Yeah.
Of
T.
T. So when now we make a restriction for x to be
The,
within here, this particular one will take
okay.
effect.
Okay.
Because none of x minus x naught will be less than what? Will be less than delta. Remember that T is taking this place to this place. So this is where, somewhere here, T of x naught will land. Are you with me?
Okay.
Good. And then within this T of x naught, if we now look at this, assuming that I look at M delta,
So that's
then we can look at this particular,
Oh.
images of
we can look at this ball. You understand? So those points, our expectation is that for any x that satisfies this condition, the image of that particular x will be in the ball centered at T of x naught,
Yes,
where is
where
what?
is this?
Where is delta? And if we go further to get what delta is, you understand? And we choose delta to be this one, then it means that the images of such points will be in the ball centered at what? Centered at T of what? X naught, where is what? That is what. So this is where, for any x that lies here,
Yes.
T of x will lie here. That's what we're trying to look at. So this E is marked onto the, why this particular one? This one is taken into this place. That's the idea. Continuing. So choosing x delta to be that, we obtain that what? That this will happen. So for any epsilon bigger than 0, there exists what? There exists a delta, which is equal to what? Epsilon over m plus 1. Such that, and is greater than 0, such that for any x in A satisfying norm of x minus x naught less than delta, then norm of T x minus T x naught will be less than what? Epsilon. Which means that what? This is equivalent to what? T is what? Continuous. Continuous at x naught. So T is continuous at x naught. And since x naught in A is arbitrarily chosen, we conclude that T is what? Continuous. Is continuous. And now, this one clearly, continuity of T at arbitrary x naught in A tells us that T is continuous at what? Origin.
Yes, okay, origin.
Because if x naught,
The third one.
if x naught is chosen to be 0,
Mm.
then you see that T is continuous at 0. So next, we show that I implies what? I. That is, we show that T continuous implies that T is continuous at what? At the origin. That is, we show that continuity of T implies its continuity. Its continuity at 0. Well, this is trivial. I implies I trivially follows since continuity of T implies continuity of T at every point of what? Of E This in particular implies continuity of t at what? At 0. Next, we show that I implies what? Implies IV. What does I? That is I says what? Suppose T is continuous at what? At 0.
Yeah.
We show that T of the unit ball centered as the ball centered as 0 radius is what? Is bounded. Is bounded. So that the image of that ball is bounded. Please, this ball, this thing I'm writing is a closed unit ball. What do I mean? That's by the closed unit ball. Recall what we mean. Recall that. I say recall that the 0 in E is nothing but the collection of all. Let me say all U in what? In E. So that what? None of U is less than or equal to 1. That's what it stands for. So we want to show that the image of that ball under T is what? Is bounded. Note, T of B by E 0 bounded. There exists a constant k greater or equal to 0, so that for any u I pick in B, but is that is in B of 0 bar, which I have that norm of T of u in X evaluated is less than or equal to k. This is what it means that the image of that ball is bounded. Note also that T continuous at 0 means that for any sequence, say xn, n equals 1 to infinity in E, such that Sn tends to 0 as n tends to infinity, we have that T of Xn tends to what? T of 0, of course, which is 0, as what? As n tends to what? Infinity. Please want to be very careful here. T of 0 is already mentioned earlier, but it's good we know. T of 0 is 0. Yeah. Because T is what? The linear map. That's one of the properties of the linear map. So we require continuity at 0, we mean sequential response. So we have that T of Sn goes to T of 0. That's what we mean by what we should the consequence of being continuous at what? At 0. And I'll make use of it. When I say means, it means that what? T is continuous at 0 if and only if for any sequence that behaves like this one. Now, suppose for contradiction that T of B bar 0E is not bounded. Suppose this is the case. Norm of T of what? UK. Now, but if this is the case, it means in particular, that for any natural number I pick, is of course greater or equal to 0. Yes. There exists what? Un. in what? In the
In B.
board,
Close book.
so that what happens? So that what?
No.
When you evaluate the norm of T of UN, we'll get something that is greater than what? Is greater than N. Clear? That's all. Is greater than 1. You know why? By the property of the norm, I can take 1 over N in, and also by linearity of T, we can get this
Yeah.
scalar. Now, setting Yn to be equal to 1 over N UN, we obtain that norm of Yn is equal to what? Is equal to 1 over N norm of UN. Yes. If I set Yn to be this, I'll get the norm of Yn is 1 over N norm of UN. Do we agree?
Okay.
This is norm of
Yes.
Yn in E is this. This, remember, this norm is where?
X.
Okay, follow me. So I'll get that norm of Yn is equal to 1 over N norm of UN. But this is less than or equal to 1 over N. Less than or equal to 1 over N. Since UN is in the
Close unit.
good. Since UN is in the board, centered at 0. In E, that's really close unit board. And this is for all N in N. Yeah? For all N in N. So what have I got? What I've got is therefore that norm of Yn is what? Norm of Yn is less than or equal to what? 1 over N. And not only that, norm of Yn less than or equal to 1 over N tells me again that not just that Yn goes to 0, but that Yn also belongs to the unit board. Because 1 over N is less than or equal to 1. This by sandwich theorem implies that Yn goes to what? 0. So I'll say,
Yes, yes.
thus, this is for all N in the set of natural numbers. Thus, to infinity is such that Yn goes to 0 as what? N goes to what? Infinity. So what this means is that we created a sequence that converges to what? To 0. But what happens? But norm of T of Yn is equal to what? Norm of T of 1 over N UN. And this is what? Greater than what? 1. Of course, this is a contradiction. A contradiction. What does it contradict? Contradicts the fact that it is continuous at origin. Because the continuous at origin means that what? Whenever you get a sequence that goes to 0, then the image of that sequence will also go to what? To the image of 0, which is 0. For this particular case, we have a sequence that goes to 0, but the image has no chance of going to 0 because the norm is bigger than 1. I don't know if you get my point. This is bigger than 1, and there's no chance of going to 0. Going to 0 means that given epsilon bigger than 0, there exists n epsilon, so that for n greater or equal to n epsilon, this will be less than epsilon. For this bigger than 1, for all n in the set of natural numbers, says a lot. Says that this has no chance of going towards 0. In fact, the sequence is bounded away from 0 by 1. Can go to 0. For k greater, this is the negation of the fact that this is not bounded.
Yeah, this is not of the yes.
For all k greater than or equal to 0, there exists uk here for which this will happen.
Yes.
And if this is happening for all k greater or equal to 0, it will also happen for n in n, because each n in n is greater or equal to 0. So for each n in n, which I have a sequence a un here for which this will happen.
And that's where the sequence came from.
From that un, we constructed that little modification, and we got this. So if I now set yn to be this sequence, we examine its behavior. And the behavior of this is that can be estimated by this. And we know the property of 1 over n. 1 over n goes to 0. So this means that this being less or equal to 1 over n tells us that yn goes to 0 by sandwich theorem. You know why?
Yes.
What you get is that norm of yn goes to 0, meaning that yn goes to 0. Fine. Good. Or even if you don't say by sandwich theorem, you can use the classical definition of convergence. If this is less than epsilon, then this will be less than epsilon. But this less than epsilon, you can find n epsilon using that. Fine. So we get it. So this sequence we generated is a sequence that goes to 0. But this happens. And this happens means that what? Means that
actually means that T of y
the T of yn is cut away from
yes, and which means that it is not continuous.
It's not continuous at 0. So it's a contradiction. Okay, good. And hence, what is our conclusion? Hence, the image of the unit ball, the unit closed ball, is what? Is bounded. Is bounded. We show that IB implies what? V. That that boundedness
image
boundedness of
image
T of B bar is 0 implies what? Implies T is Lipschitz. Recall. Want to recall. Recall that. Okay, man. T from B to X is Lipschitz. If and only if there exists a constant m greater or equal to 0. So that for any x or y in the domain of T, subset of A, what we have is our norm of T of x minus T of y is what? Is less than or equal to norm of x minus y. This one is in P. This is what we mean by the operator is Lipschitz. So we want to show that if T is the linear map and the image of the ball open, those closed ball bounded implies that T is what? The Lipschitz map. To do this, so what we need to do is to find a constant L for these circles. X, Y, and A. If X is equal to Y, then T of X will be equal to what? T of Y. Are we together? T of X will be equal to T of Y. So that what happens? So the norm of T of X minus T of Y is equal to 0, which I can still write as equal to what? Norm of X minus Y. Is it not true? Because we can do this because what happens? Because X is equal to Y.
Yeah.
So, in this case, if this is the case, then trivially, there exists what? L greater or equal to 0, such that norm of T x minus Ty in x is less than or equal to L norm of x minus y. If this is equal to this,
Because L is greater than or equal to 0.
L is greater or equal to 0. This is 0, less or equal to 0.
Yes.
We can choose L to be any constant.
Yes.
Huh? Nothing stops us from choosing L equals even 0. You understand? Any constant will do. Because here is 0. Here is 0. Any positive, any non-negative constant will do.
It's bigger than or equal to 0.
Okay.
Now, the next case is what? If x is not equal to y.
Okay.
Hmm? Are you with me?
Yes, bro.
Then setting ux y equals over norm of x minus y into x minus y. I can do this. So that uxy belongs to the ball
Oh, sometimes
centered at 0
the truth is
and
one.
do you know why? Since norm of u x of y is equal to 1 over norm of x minus y, norm of x minus y, and this will be equal to what? 1. And since this norm is 1 is this ball, because this ball is direction of all those for which the norm is less or equal to 1. So that thing is in that ball. Hence, since t of b but 0e is bounded, there exists m greater or equal to 0 such that for any u we pick in b 0 by e, norm of t of u in x is less or equal to m because it's bounded.
Okay.
This means therefore that norm of t of this means that norm t of u x y is less or equal to m because u x y is one of such u's here. This means therefore that what? That norm of t of 1 over norm of x minus y into x minus y is less than or equal to what? M. And therefore, what do I have from me? I have that norm of t of x minus y is less than or equal to m. This is norm e. Are you with me?
Yes.
So that will be less than or equal to what? M. This will come out, and by the time you write it, you get norm of x minus y. And this further means by linearity of t, that norm of t of x minus t of y is less or equal to what? M norm of x minus y. Remember, our job is to find a constant L for which. So choosing L equals M, we obtain that what happens? That for any x, y in E with x not equal to y, norm of t of x minus t of y in x is less than or equal to L norm of x minus y. So can we now conclude? In conclusion, this is for x not equal to y. Together with x equal to y, you find that we still have the same inequality even if x is equal to y. So I can now conclude therefore that what? There exists what? L greater or equal to 0 such that for any x, y in what? In E, norm of t of x minus t of y, x is less than or equal to L norm of x minus y. So this completes that part. So this means that the thing is what? Lipschitz. You remember combining where x is not equal to y as well as where x equals to y. In all, we get it for all x, y, and e. I don't have. B implies I. I hope we're following.
Yes, sir.
That is, we show that T Lipschitz implies T is what? Bounded. But T is leaches if and only if there exists what?
F.
There exists
K.
a constant L greater or equal to 0 such that for any x, y in E, we have our norm of T of x minus T of y is less than or equal to
L norm
L norm of x minus y. Yeah?
Yes.
Thus, there exists L greater or equal to 0 such that for any x in E, for y equals 0 in E, this one thing,
Mm.
is true for all x, y in E.
Okay.
It will be true for all x in E,
Mm-hmm.
and for y equals 0.
Okay.
For y equals 0 in E, norm of T of x minus T of 0 will be less than or equal to L norm of x minus 0.
Mm-hmm.
But linearity
Okay.
of what T implies that T of 0 is equal to what?
Zero.
0. So, there exists L greater or equal to 0 such that for any x we pick in E, norm of T of x is less or equal to L
Okay.
norm
Norm
of
of
x. What does that mean? This is
E.
what does that mean? Hence, T is what? Bounded.
Bounded.
T is a bounded line.
This one is easy. This one.
It looks easy. Looks easy. So when we take a particular case where y is 0, we conclude that. So you see that all those things are connected.